David Spears, Civil Engineering Instructor at Texas Tech University, talking about CE 2301 statics. Today we're covering friction, another aspect of it. The friction on flat belts, ropes, and cables as they pass over a fixed shaft. Okay, so the basics of it are, drawn in black is the shaft. The cable, or the belt, is drawn in red. And the angle of contact is this theta angle, the amount of contact area is an arc that the belt makes contact with the shaft. And then, very important aspect of it is the friction force between the shaft and the belt. And so you've got to always look at whichever is the direction of motion or impending motion to determine what the direction of friction is. Then from that you can tell which one's going to be larger and smaller of these tension forces. So in this case, in this drawing I've shown the direction of the belt motion is this way, to the left. So the direction of the friction is opposite that, to the right. And you always want to, this is the key part of analyzing these problems. The textbook shows the math, which is very beautiful, and you derive this formula. T2, the larger force, is equal to T1, the smaller force, times this multiplier, E, which is that number 2.7183, continuing, to the mu sub s times theta power, where mu sub s is the coefficient of friction, theta is the contact angle of the belt with the shaft measured in radians. So real quickly I want to say that this is not like a pulley. In a pulley we assume no friction, and so the tension force on either side was unchanged. It was the same. This is not a pulley. This is a fixed shaft, and so there is friction there. So one of these forces is going to be larger than the other one. Best way to do this is to look at an example. I've got a simple example here of a 10 kilogram weight suspended from a cable or a flat belt, passing over a shaft, and then I'm exerting a force P horizontally to the right to do different things to the weight. The coefficient of friction is 0.35, and the angle, I'm giving you the diameter, the radius of the shaft, but it really doesn't make any difference. What matters is this angle of contact, theta. So first part is to find the P force to prevent the 10 kilogram weight from dropping. So once again, let's say the key factor is this: what's the direction of motion? If it's prevented from dropping, the motion of the belt would be to go down. So I've drawn in green there. The friction force is opposite that direction, so it's up, so it's clockwise. And so it helps the P force resist the weight. Another way of looking at it. So I write that in a sort of an equation form. The weight here, suspended from the cable going down, is equal to the P force pulling plus the friction force, because the friction force is in the direction of P. So P is the smaller force. It's the T1 force in this equation. And so I can solve for P is equal to T2 divided by this multiplier, E to the mu theta power. Plug in the numbers. Of course, I've taken my 10 kilograms and made it 98.1 newtons because I'm dealing in forces. 98.1 divided by E to the 0.35 with the coefficient of friction, and pi over 2, which is a quarter of a revolution in radians, comes out to be 56.6 newtons to prevent the weight from dropping. So you can see I've got 98.1 down. I'm helped by the friction, so I only have to exert a 56.6 Newton force to keep it from dropping. Now I want to find P to raise the 10 kilogram weight. Well, looking at this little drawing here, Now, if I'm trying to raise it, the motion of the belt is going to be to the right. So the friction force is going to be opposite that. It's going to be counterclockwise. And so the weight plus the friction is equal to P. The friction's in the opposite direction of the P force. So P is the larger force, T2. P is equal to this formula. P is T2 in that formula. So it's 98.1 e to the 0.35 pi over 2 is 170 newtons to raise the weight, which makes sense. I've got to overcome friction plus pull the weight up, so I'm looking for a bigger force. Here, friction is helping me keep the weight from descending, so it's smaller than the 98.1. So basically, the procedures for these these flat belt rope cable problems is to determine the direction of the motion. Draw a little free body diagram. Put the friction on there in the opposite direction from the motion. And then reason it out, or write a little equation. Determine which T force is smaller and which is the larger. Then I've got to also figure my theta contact angle in radians, and then it's a simple calculation from there.